Okay, so I had a couple people come by. They wanted to do number 12. We're going to do number 12. So what does number 12 ask us to do?
We're recording now.
Yeah, we're recording.
I'm caught. Okay, so it says it can consider a buffer made from 1.0 moles of HF and 1.0 moles of F minus in 1.0 liters of water.
Okay. So the concentration of the hydrofluoric acid is 1 molar. The concentration of the fluoride ion is 1 molar. Part A is pretty straightforward. Calculate the pH. Since we have 1-to-1 ratio, we can use our Henderson-Hasselbalch, which is going to be pH equals pKa plus log F minus over HF. Something like that. Because our F minus and our HF have the same concentration, we're at what special point? Midpoint. We can go ahead and say the log of 1 is going to be equal to 0. We're at this point where pH equals pKa. Does anybody have the pKa for hydrofluoric acid?
Give me 1 second.
We'd have to look that up. I think it's something like 1.3, 1.4.
Pressure's on right now. Okay.
I know, I'm recording. Come on.
I'm sorry.
Plus, I have to go to class.
Oh no.
7.2 times 10 to the negative 4.
No PK.
Yeah,
3.17.
3.17. Okay,
Yeah,
so there's that was the Ka. Very close, right? Just taking the negative log of that number and we're good. So that's part A. What's part B?
Okay, part B.
Right, the neutralization reaction
Occurs when HCl is added.
So when HCl is added, we have to think, is HCl going to react with hydrofluoric acid? Is it going to react with fluorine ions?
Fluorine.
So what's the important part? When we add HCl, what's the important thing we're adding? Is the chlorine important?
No.
Is the H plus important? Yeah, is H plus, could H plus react with fluorine if we've got a weak acid?
Yes.
Yeah, so our neutralization reaction would be essentially whenever we're in a buffer situation, we've got kind of a common ion effect, right? So adding H is going to be a common ion to this. So I'm going to have F minus plus H3O plus goes to HF plus H2O, right? That's kind of like an acid-base reaction. I've got my Bronsted-Lowry base, I've got my Bronsted-Lowry acid. This is going to accept a proton, this is going to donate a proton. I make my conjugate acid in hydrofluoric acid and my conjugate base H2O. Part C asks us to do the same thing, write the reaction. And notice the key term in this is the reaction. So we want to think about what reacts. And this asks us to do it for sodium hydroxide. And again, we think, okay, what's the important part? Sodium?
No.
No,
OH
of course not. The OH minus is important. Is OH minus going to react with F minus?
No.
So it's going to react with the HF. So I'm going to have HF plus OH minus goes to F minus plus H2O. Now all my reactions are wrong because I forgot my states of matter. Let's go ahead and put those in. Right, but you notice as we start to do more and more chemistry, just the context does a lot to tell us about the states of matter. But to get credit on an exam or a quiz, you need the states of matter in there. So I'll make sure I do it when I'm doing it as well. Unless I'm in a rush. Happens in class sometimes. So that's B and C. And notice it just took a little bit of thinking. A little bit. It's not a math problem. We've done all the math we're going to do. It's just thinking about, okay, how do I do one thing or another? What's part D? I think this is where it gets interesting.
D is calculate the pH of the buffer after 0.1 moles of hydrochloric acid is added.
This is where we get to use that trick I showed you in class on Monday. So you notice we're adding acid. So we're going to have a reaction. We're going to have reaction B. our fluorine minus is going to be reduced by how much we add, and we're going to create that much hydrofluoric acid. So I'm going to go ahead and put this in terms of moles. I've got 1 mole here. I've got 1 mole here. Essentially, what I'm doing is in my, I'll do a quick little aside here. Assuming I'm not going off the screen. Not quite.
No, you're good.
Okay, so we've got our same reaction from B. We've got F minus plus H3O plus goes to HF. I'm not going to worry about the water. This doesn't matter right now. I've got start, reaction, excess. I've got 1 mole. I've got 1 mole. So notice that 1 mole that I put here is the start. My reaction, how much H3O plus am I adding in this case?
0.1.
I'm adding 0.1, so when I do my reaction, I'm going to have minus 0.1 plus 0.1. And I'm going to put that in over here. I'm going to have minus 0.1 for my F minus. I'm going to have plus 0.1 for my HF. Adding acid removes some of my conjugate base and produces some of my weak acid. Do you remember this from class on Monday? Right, we had that really kind of nice one where, because it gave us everything in moles, it's actually a little bit easier than what we did in class on Monday, because we don't need to do molarity times volume a whole bunch of times. Now, this is also a little bit harder than what we did in class on Monday, because notice, in class, we always started with 0 conjugate base, and here we've got a non-zero value for our conjugate base. So this is one of those examples where I'm adding to a buffer, so my starting conjugate base, my starting weak acid are both not 0. But at this point, we've got our pKa. Can you solve 1 minus 0.1? We're going to have pH is equal to 3.17 plus log 0.9 over 1.1. And I think that sets us up pretty well to do part E as well, where E is your adding base. Now, we're adding acid, so we expect the pH to go down, and we were at the midpoint already, so we expect the pH to go down from 3.17. I'll admit something now, and I'm going to admit it on video, which is a little terrifying. I have this problem I've put on midterms in the past that everybody gets wrong, because I do this problem, but we don't start at the midpoint. And it freaks people out. I'm like, let's say we're at a pH of 4 and you add some acid. Then you end up with a pH of like 3.8. And they're like, but it's above the midpoint. It's like, but you didn't start at the midpoint, right? It only has to be, it can be above the midpoint if you're adding acid, if you're starting above the midpoint. So, but since we're at the midpoint, adding acid should bring our pH below the midpoint. 3.08. Can you do, now, with this in mind, this is where it gets really neat. When we start getting comfortable with this equation, it starts to become very easy to do a lot of these problems. So what is part E?
E just says 5 moles. Yeah.
Ooh, 0.5 moles of HCl? How fast can you do that? You're going to have 0.5 over 1.5. Should be pretty straightforward. You can also start to see where you can get a little bit in trouble. Because what if I said, instead of 0.5 moles while you're doing that calculation, what if I said add 0.99 moles of HCl?
Wait, would that just be the same? If you're adding, like, would it just be your pKa?
No, because it's going to be 1 minus 0.5 and 1 plus 0.5.
Oh, never mind.
So you're going to get 0.5 over 1.5.
Right, okay.
Right? And in our buffer system, the other thing you'll notice is the starting conjugate base weak acid total is always going to be our same total, right? 1 plus 1 always adds up to 2. No matter what you do, you should end up with something that adds up to 2.
I got 2.69.
Great.
I did also.
Does it keep going after that?
Yeah, it has one more part, and it's how many moles of HCl do you need to add to lower the pH by 1 pH unit?
What's the pH at 1 pH unit lower?
Mm-hmm.
What is that value?
2.17.
2.17.
Oh, okay. You just work backwards.
Yeah, right. So I know my midpoint's 3.17. I'm going to get 2.17. Now I'm just going to, instead of having 0.1 here and 0.1 there, I'm going to have moles of acid. I'm going to have moles of acid. And I'm just going to solve for moles of acid. That's for this part, for part F. And the only difference between doing this and what you do in the buffers lab is you have to take into account the fact that you've got molarity and volume rather than just moles. But other than that, it's the exact same thing you're doing in your buffers lab this week.
So how would you, for like your moles of acid, how would you do that on the calculator?
Oh, that's what you're solving for.
Yeah.
So the way you would set this up is you'd have pH is 2.17 because that's our target pH.
Yeah,
It's equal to 3.17 plus log of 1 minus, I'm just going to call it x,
yeah.
and 1 plus x.
Mm-hmm.
And then you just do the algebra. I'm going to have 2.17 minus 3.17 is negative 1. 10 to the power of negative 1 is?
Oh, 10 to the power. That's right.
Yeah.
Math.
0.1 equals
Right.
1
Okay.
plus x. Solve for x.
Mm-hmm.
And that's how you do that problem. Now, in this, I want to point out one more thing. The place where we could get in trouble is, what if I said add 0.95 moles of acid? Could you do that calculation with 0.95 moles of acid?
0.95 moles.
Right? If I just said 0.95, you'd get 0.05 on top, you'd get 1.95 on bottom.
Mm-hmm.
Totally works mathematically. However, notice, at that point, you're actually going to be outside of your buffer range. Your excess small approximation might start to fail.
Mm.
So we have to have that extra kind of thought when we start doing this. We can't just mindlessly do the math, right? Math is not hard. It's the concepts behind the math. And once you get within 10%, once you get to within 90% of it, you start to get to that point where you're going to start to get to the edge of your buffer range and the place where the excess small approximation might start to fail. Hopefully that's helpful. I'm going to go ahead and post this video and then I have to run to class. You'll notice problem 13 kind of asks you to do the same thing, right? It's still using that same specialized, I don't know what to call it, the Henderson-Hasselbalch with stoichiometry. That equation. Problem 14 is exactly like your lab. I don't think problem 14 will be on the midterm, but everything else is fair game.
Okay.
Cool. Okay. See ya.